Hello again, everyone. It's time for our next topic, hypothesis testing. Extremely important for any science. Any science is going to have, it typically involves empiricism. Empiricism involves the testing of hypothesis by collecting data, and psychology is certainly no exception to this. And really, as you'll see, that's one of the main purposes of statistics is to test hypotheses here. So, this is another topic common to all inferential statistics. As I think I pointed out before, inferential statistics are all about inferring something about the population based on a sample, statistics that you gather from a sample, or many samples. Hypothesis testing integrates many of the other topics that we have covered or will cover soon. Principally, hypothesis testing uses probability and the sampling distribution of a statistic that we've learned about before to make decisions about a parameter. Hypothesis testing is the process of testing tentative guesses, that's one way of putting it, tentative guess or just a hypothesis, about relationships between variables in populations. These relationships between variables are evidenced in a statement called a hypothesis about a population parameter. So, for example, you might propose that the mean, the average for a particular group is going to be better or worse than the average for another group on some measure. So let's say you're looking at GRE scores. You might predict that a certain group, let's say college graduates, are going to do better. They're going to have a better average score than high school graduates on the GRE, and they probably should. So that would be a hypothesis that you can test with certain statistics that we'll be getting into in this course. So an example here that we've seen before, the IQ of deaf children example. So you might ask yourself, are the deaf children in your sample, do they have lower IQ than the population average as a whole? And I'll point out in a moment why you might predict that. It doesn't really have to do with intelligence. Okay, are the deaf children, do they have lower IQ based on your IQ measure, or are they closer to the IQ average? And the average in the population is a mu of 100 and a sigma squared, or a variance of 225. So is the Xbar, is the mean of your sample of deaf children, if that mean is 88.07, and it's based on a sample of 59, let's say, is that significantly lower than 100? Okay, so it's numerically lower, but the key with hypothesis testing is that you're asking the question, is it significantly lower? Is that a reliably lower number? And so this is just breaking down what we're going to be really getting into in today's lecture, but I'm showing it all to you right off the bat. So what you need to do is compute z, which is, and we've seen this before, x bar minus mu divided by the square root of sigma squared divided by n. So you work those numbers here and you get negative 6.11. That's your z value, and we'll see a bit later in the lecture what that means, kind of how to picture that when you're looking at a sampling distribution. So what you want to do is find the probability that x bar is less than 88.07. I guess it should say less than or equal to 88.07. In other words, the probability of z less than or equal to negative 6.11, which is what we already found. And what you find is that probability, based on looking it up in a table, table A.1, appendix A.1 in your textbook, you get a p of 0.00003. Actually, now that I think about it, this is such an extreme z value that I think it's off the charts of your appendix. So don't look at the appendix yet. We'll be getting to more reasonable z values for you to look up a bit later in the lecture here today. So anyway, this extreme z value leads to a very low p value. So what that means is that the probability is very low. It's very unlikely that the deaf children in your sample come from a population with, come from the general population with that mu of 100 for IQ. So we decide that their mean is actually lower than 100, and that therefore the children have lower IQ scores. Now, here's where I'm pointing out, this does not mean that I'm saying that deaf children are less intelligent, not at all. Rather, a large portion of IQ has to do with verbal ability. And deaf children, if they're born deaf, typically they learn, in this country, of course, American Sign Language, ASL, rather than spoken English. And so that that's going to just lead them to have an artificially lower IQ score. And that's all I'm talking about here. Okay, so some key terms to remember here as we go forward. A test statistic is a statistic used only for the purpose of testing a hypothesis. So for example, Z, we'll get into several more in this course, like T. And there are always going to be assumptions built into any test statistic for testing hypotheses. These are conditions placed on a test statistic necessary for its valid use in hypothesis testing, and unfortunately a lot of researchers ignore these hypotheses, but it's important to keep these in mind to make sure you're using the correct test statistic based on your samples, based on your research design, and other aspects. For Z, the assumptions are that the population is normal in shape, and we're going to see that what's called the normality assumption. Many times, a lot of the test statistics have that normality assumption where you're assuming you're dealing with a bell curve. Another assumption is that the observations are independent. Okay, that's also a very, very common assumption. So that there are other test statistics for dependent observations. If you have, let's say, a pre-test, post-test sort of thing, as we'll see later in the course, one test statistic for that is the dependent samples t-test. But for now, we're going to assume that our observations are independent. You have a null hypothesis. This is the hypothesis that you test directly for what's called NHST, null hypothesis statistical testing. And that's what I'm talking about, is testing a null hypothesis, and I'll get more into that later in the lecture today. And you also are going to have an alternative hypothesis where we put what we actually believe, okay? It's designated H1 or H sub 1. So both the null and the alternative are stated in terms of a parameter. So let's kind of see how this works here. Well, some additional terms first. Significance level is the standard for what we mean by a small probability in hypothesis testing. This has to do with the p-value, but really it's what we're talking about is an alpha level is what it's called, which is typically 0.05 in psychology and other social sciences. It's easy to confuse this with the p-value. It's not the same thing as p-value. Rather, you compare the p-value that you get with the alpha significance level. Okay, so it's a common misconception where students think that p-value and alpha are the same thing. They're not. Okay, we'll get into this more a bit later here. I'll be talking about directional versus non-directional hypotheses, which directly correspond with one or two-tailed tests. A directional hypothesis requires a one-tailed test. A non-directional hypothesis requires a two-tailed test. I'll also be talking about critical values and rejection values, decision rules, two kinds of decision rules, the critical value decision rule and the p-value decision rule. And by and large, you're going to see p-value decision rules in the literature. Okay, so let's start off with the null versus the alternative hypothesis. And I'll be continuing with this example of IQ and deaf children, just for the sake of simplicity here. So again, we're starting with an alternative hypothesis here. We believe that the deaf children will score lower on the IQ test because English is not their native language, rather American Sign Language is for your sample. So you're expecting that their mean is going to be less than the population mean, or mu, of 100. So that is our alternative hypothesis. Okay. So the null hypothesis in this case, because we have a directional alternative hypothesis, it's specifying that we expect that your sample of deaf children, that their IQ is going to be lower than 100. That specifies a direction, lower. So that makes the null greater than or equal to 100. Okay, so the null is the opposite of the alternative hypothesis. In terms of significance level here, again, we're talking about alpha. The significance level is the small probability used in hypothesis testing to determine an unusual event that leads you to reject the null hypothesis. And as I said, it's symbolized by alpha. The value is almost always set at 0.05. So when in doubt, assume it is 0.05. As we'll see, this is modified slightly if you're talking about a one-tailed test versus a two-tailed test. I'll get into that a bit more later in the lecture here. The value of alpha is chosen before data are collected. That's very important so that researchers aren't tempted to kind of tweak things unethically after they get their data. Rather, you have to say right off the bat, before you run your experiment, say, I have a, for example, I have a two-tailed hypothesis. Sorry, let me back up. Let's say you have a one-tailed hypothesis. That is most common, is that you're predicting a direction. Okay, so that, let's say you're predicting that your sample of deaf children will have a mean IQ of less than 100. Okay, that means that your alpha is going to be set at 0.05, and you have to say that before you collect any data. And then if your null hypothesis is rejected when alpha equals 0.05, here are examples of what you would actually write based on APA style. So the writing method for the American Psychological Association is what we're going to be utilizing in this course, and what you're going to be facing in most of the courses that you have here is APA style. So let's look at what that would look like. The IQ of deaf children, mean, that's the symbol for mean for APA style. So they don't use Xbar, they use this capital M, and it has to be italicized if it is a statistic symbol. Mean equals 88.07, so that's what we're saying that is what we're getting for the IQ average for our sample. Is significantly lower than 100, which is what we're comparing it to, the average in the population. And that's the z-value that we got, and that's the p-value as a result of that extreme z-value. So as you might recall, the p-value was actually 0.00003. Okay, APA style does not require you to state an exact p-value if it's that low. Rather, they want you to just say, hey, it's less than 0.01 or less than 0.001. And it's important to state sometimes that you have a one-tailed test. It's typically assumed that it's a one-tailed test. Okay. So let me continue now with directional and non-directional hypotheses. Directional hypotheses specify a particular direction for values of the parameter. For example, we expect that the mean is less than 100, like for the IQ of deaf children here. And here's what it looks like, the null hypothesis versus the alternative. Non-directional hypotheses do not specify a particular direction for values of the parameter. So you can say, maybe you have a sample of deaf children and you really don't know if they're going to be having a lower or higher IQ than the population. You might predict it could be lower for some reason, it could be higher for some reason. You really don't know. If that's the case, then you have a non-directional hypothesis. The null is that that they're not going to be different from 100, or equivalent with 100, and the alternative is that they're just not going to be equivalent with 100. Okay, you don't know if it's going to be higher or lower. Another example, suppose you believe that dancers are more introverted than other people. I don't know why you would predict that, but it's possible. You have a sample of 26 dancers, and know from this age group with your male-female ratio that the mu is 19.15 on a measure of introspection. So what your hypothesis is, your null, is that your sample is going to be less than or equal to 19.15, but you're really predicting, your alternative hypothesis is that they're actually going to be higher on this introversion scale, so that your sample is going to be higher than the average in the population, the mu of 19.15. Okay. So I might come back to that example a bit later here. Okay, so one-tailed test is a statistical test using only one tail of the sampling distribution of the test statistic, and I'll be showing you several graphical depictions of this. A two-tailed test is a statistical test using both tails of the sampling distribution of the test statistic. Critical values are values of the test statistic that cut off alpha, or alpha divided by 2, in the tails of the theoretical reference distribution. Now, we'll get into this more, I promise, and you'll be able to see how this works. But alpha, as I said, is 0.05, but you do need to divide by 2 if you have a two-tailed test. Okay, just something to keep in mind for later. Rejection values are the values of the test statistic that lead to rejection of your null hypothesis. So let's see how this works here. Here I have a standard normal distribution. I apologize, I have a cold, so I need to be sipping my tea here. And this is for a two-tailed test. So you see alpha here and alpha there. It's 0.05, okay? You need to divide by 2 to make it 0.025 to designate the fact that it's a two-tailed test. You're dealing with both tails because you're saying, hey, what example do I have here? Okay, so this is back to the deaf children example, although this is the non-directional hypothesis. You're saying that maybe my sample of deaf children will be significantly higher than 100 for IQ or significantly less than 100. You really don't know which one. So you're dealing with either tail. You're predicting that essentially your sample of deaf children are either going to be in the upper tail, they're either going to be significantly higher than the mean of 100 in the population, or they're going to be significantly lower. They're going to reside somewhere down here compared to the mean of the population. So the mean here is 100 if we're talking about IQ, and these are z-values designated an alpha level of 0.025. Okay, it's important to keep this in mind. There's a different level. It's actually 1.65 for an alpha of 0.05, and that's what you'll commonly see. But here we're dealing with a non-directional two-tailed test. Therefore, with an alpha of 0.025, you need this critical value. You might ask where the heck that comes from, 1.96. Well, it has to do with certain characteristics of the standard normal distribution. So it's an assumption, okay, to have that. It's called a z-crit, or a critical z-value, okay. So again, this is a two-tailed test. The critical values, as I point out, are negative 1.96 and positive 1.96, and therefore rejection values are greater than or equal to 1.96 or less than or equal to 1.96. Just everything I already pointed out. You're wondering if your sample is going to be in the lower tail or the higher tail. They have to be that extreme in order to argue that it is a significant difference from the mean of your population. Okay. If they're not in one of these tails, then they're part of this overall bulk of the distribution, and they're really not that different from the average. They're not that different from the bulk of your distribution if they're just somewhere in here. So you need to show, hey, they're extreme. They're either here or there. They're here if they have significantly higher than normal IQ. They're here if they have significantly lower than average IQ. Okay, so let me get into a one-tail test here. So this would be if you're saying, okay, listen, the deaf children, they don't know spoken English. Part of IQ testing involves a knowledge of spoken English. Rather, they have a knowledge of American Sign Language, and so that might artificially push their IQ scores down. So you might predict that they're going to have lower than average, okay, IQ scores. So again, the average IQ would be 100. I know that says 0. That says 0 because we're talking about the standard normal distribution. But if this was if this were IQ, then it would be 100. But this is in terms of z-values here, and we're dealing with an alpha of 0.05, which, as I pointed out before, involves a z-crit value of 1.645 or just 1.65, and negative 1.65 because we're dealing with the lower tail here. So you're predicting that your sample of deaf children are going to be somewhere in here when it comes to their IQ scores. So it's a one-tailed test. That's your critical value, and your rejection value, the one that you're going to be, basically you're going to obtain a z-value and compare it with this z-critical value. It's the same thing as getting a p-value and comparing it with your alpha value. Okay, you're hoping that your p-value is going to be less than alpha of 0.05, and the exact same way you're looking for a z-value, obtain z that's less than negative 1.645. Okay, back to a two-tailed test here. Sorry, I'm jumping around a bit, but notice that the z-crit values have changed again, back to 1.96 and negative 1.96, because again, we're talking about a different alpha value here, 0.025. So for a two-tailed test, you reject the null hypothesis if the observed z value, z obtained, z observed, it's sometimes called, or just z sub Xbar. You're hoping, if you have a non-directional hypothesis here, you're hoping that it's going to be either less than or equal to negative 1.96 or greater than or equal to 1.96. Same thing as predicting that your p-value is going to be at or less than 0.05. Okay. And I'm not showing you how we got that number, but basically you just run the formula that I've given you before for calculating z. Let's say you get a z-value of 3.0. Well, here's where it is on this distribution. You can see clearly it's greater than 1.96. Therefore, you reject your null hypothesis. They're not similar to, they're not at all close to the average of 100 in your population. They're not part of this bulk part of the distribution. They are in the extreme tail here. Therefore, your z-value, your obtained z-value, z sub x bar, is greater than your critical z-value of 1.96. Same thing as saying that p is less than 0.025. Okay. Which I guess I'm emphasizing on this slide here. Right, so the actual p-value there, which you can obtain by looking up z of 3.0 in the back of your textbook, Appendix 8.1. You get a p of 0.0026. The one that's actually in the table is half of that because it assumes a directional test. Because this is a non-directional test, a two-tailed test, you need to multiply. So you need to look, okay, so you look up z of 3.0, you look for the column that says smaller proportion because you're talking about the tail here, but then you need to multiply by 2. Trust me, if you do that, you will get 0.0026, okay? Or it might be 0.0027. Either way, same thing. I'm just trying to point out where the z is and also where the p-value is. Okay, the p is less than 0.025. It's quite a bit less, so it's in an extreme tail here, extreme part of the tail. So you're rejecting your null hypothesis because p is less than alpha. Now, what about another example here? I think we've seen this one before. Sorry, that should say now use a one-tailed test rather than no. Okay, so again, here's where we're talking about you're just hoping that your sample of deaf children will be significantly above. I'm sorry, this is a one-tailed test. You're expecting that they're going to be significantly less than 100. And this was based on other numbers here is how we got this z-value. I think I presented this earlier in the lecture. Anyway, just pointing out how extreme this z-value is. This is the one that had that p of 0.00003, way less than 0.05, way less than this critical value of z. In fact, it would be way out here. I mean, talk about extreme part of the tail. You can't even see it as part of the normal distribution anymore. So yes, if you were to actually get this z-value for your sample of deaf children, it would be very powerful evidence that they are different from the average IQ score in the population, that they're performing quite a bit lower on their IQ test, probably because of American Sign Language rather than spoken English. Okay. So again, the observed z, z sub x bar, or obtained z, or observed z, is negative 6.11. So again, you're rejecting null hypothesis because your obtained z is way less than your observed, your critical z. Okay, so now I'm going to ask that you compute z for that other example I gave you before, introversion of dancers. Now remember, you believe that dancers might be more introverted than other people. You have your sample of 26 dancers. You know that your mean introversion in the general population is 19.15 on some introversion measure that you have. So your null hypothesis is that that your sample of dancers are going to be at or below that, but what you're really expecting is your alternative hypothesis that their mean is going to be greater than 19.15, that they're going to be more introverted than your population. So are the dancers in fact higher in introversion, or are they average? So here are the numbers. I'm giving you sigma here. You have to have that. This is your standard deviation from the population. You have to have that in order to calculate z. And an x bar here. So this is what you actually obtain from your sample. Okay, so you get this number on your introversion measure, 19.79. You compare it to 19.15, and numerically it's higher, but you want to know if it's significantly higher. Okay. So the way to address that is to compute z, and here's the formula again that you definitely need to memorize. X bar minus mu divided by standard deviation, square root of sigma squared divided by n, and you run the numbers, you get 0.76. Okay, so that is your z value. Well, let's look at where this is on our standard normal distribution, or our z distribution. And what you need to do, as we've seen before, it's a directional hypothesis, so we're going to use a z-value of 1.645. We obtained a z of 0.76, which is not more extreme than 1.645. There it is on the distribution. That's where your sample of dancers are compared to the overall population. And yeah, they're not that different. They're basically fully a part of the normal, the the bulky part of the distribution here, they're not that extreme. So you did not support your hypothesis that they are more introverted. Okay, you found that they're not more introverted, even though the raw number that you got on your introversion scale was a little higher than the average in the population, 19.15. It wasn't significantly higher. Okay, so that's what I have for the lecture today. Sorry, that started over again. Well, that's all I have for today. If you have any questions about hypothesis testing, feel free to shoot me an email, and I look forward to reading your discussion posts and continuing with the lecture for next week.